Today we are explaining PhiZero, a world model built around physical language.
What problem is PhiZero trying to solve?
Many video world models predict future pixels directly. They can make a scene look convincing, but the physical rule behind an interaction remains hidden inside a large visual predictor. That is why an object may look realistic while failing to move, deform, or react as the real object should.
So the paper needs a representation of change, not just a better picture of the scene.
Exactly. PhiZero learns a compact, discrete physical language from unlabeled videos. These symbols describe how a world state changes. The model can reason over that sequence first, and only then render the resulting transition as a video.
What does the paper mean by physical language?
It is not a list of handwritten laws such as gravity or friction. It is a learned vocabulary of transition patterns, extracted from visual experience. The symbols are compact enough for a reasoner to predict, while the decoder supplies the appearance details needed to make the future video. The core factorization is shown here. Given the first frame and an action intent, PhiZero first predicts the physical language sequence C. Then it predicts the future video V conditioned on that sequence in the first frame.
Why is separating those two predictions useful?
It gives the model a place to decide what happens before deciding how every pixel should look. The first frame anchors the static appearance, while the physical language sequence carries the evolving state. That makes dynamics an explicit prediction target instead of an accidental byproduct of pixel synthesis. The full pipeline has two complementary components. The tokenizer reads a training video and compresses adjacent state changes into physical language symbols. A diffusion decoder reconstructs the video from the first frame and those symbols. Later, the reasoner receives a first frame and a high-level action intent, predicts the symbol's autogessive lie, and sends them to the same decoder.
What exactly does the tokenizer measure between frames?
Instead of pooling an entire clip into one global code, it compares each pair of adjacent latent states. A shared transition level queue from extracts features for each interval, preserving temporal order. Finite scalar quantization then turns those features into a vocabulary of discrete symbols without learning a separate codebook. In the implementation, a 33-frame clip becomes 256 physical language symbols. That is a sharp compression compared with the 44,800 continuous visual tokens used by the LAN to point to VAE baseline, while still retaining enough information for reconstruction.
How does the reasoner learn which transition should follow an action?
The tokenizer is frozen after it has encoded each training video. A pre-trained vision language model sees the first frame and the caption of the initiating action, then predicts the target symbol sequence from left to right. The captions are intentionally high-level, so they describe what starts the interaction without giving away the fine-grained outcome. The data pipeline also matters. Filtering starts from about 50,000 hours of real-world video and 1,000 hours of simulation. It produces about $10,000 for tokenizer pre-training, 5 million for second clips for tokenizer fine-tuning and reasoner pre-training, and 1 million motion-rich clips for reasoner fine-tuning.
Does the representation improve physical outcomes, or only compression?
It improves the physical evaluation as well. On Physics IQ Verified, PhiZero scores 41.2 IQ score, above the previous best-listed score of 39.5 from Cosmos 3 Super. Its spatial IOU is 58.2 and its spatial portal IOU is 36.8, the strongest values in those columns. The same pattern appears on generation benchmarks. PhiZero reaches 3.01 physics score and 2.97 overall on PhiGround, and 4.88 physics adherence with 8.19 total on world model bench. These scores say the gain is not just visual quality, the generated state changes follow physical constraints more closely. The qualitative comparison makes the difference easy to see. When a tennis ball hits a rubber duck, the baseline can show a plausible-looking scene while leaving the duck unchanged. PhiZero produces downstream effects such as object displacement, deformation under gravity, chain reactions, and changing shadows.
Can the learn sequence also judge whether a video is physically plausible?
Yes. For understanding benchmarks, the reasoner encodes both videos in a matched pair and assigns each sequence a likelihood. The video with the higher likelihood is selected as the physically valid or causally natural one. PhiZero reaches 56.3 for overall on INT, is to end an aggregate rank of 2.0 on YoCausal, showing that the representation can support discrimination as well as generation. Ablations explain where the gains come from. Removing the diffusion decoder drops BSNR from 28.9 to 26.6. Replacing the transition level Q-former with a global one drops it to 28.2, and removing pure noise warm-up drops it to 27.9. Each component helps the bottleneck represent transitions instead of relying on shortcuts.
What can PhiZero do beyond the benchmark tables?
Because the intermediate sequence describes state change separately from appearance, it can be used as an interface. The paper demonstrates interactive rollouts under sequential controls, action condition simulation, physically realistic video generation, and zero-shot transfer of motion across different appearances and embodiments.
What remains unresolved?
The symbols are empirical rather than interpretable physical laws, so they are not directly grounded in variables such as force or mass. Observational video also misses hidden or ambiguous events, including tactile interactions and microscopic dynamics. Finally, the current model and data are still small relative to the diversity of the physical world, and the current fixed duration clips do not yet provide long horizon prediction. The paper's main contribution is therefore a change in where the model reasons. Instead of asking a video generator to hide all dynamics inside pixels, PhiZero learns a compact transition language, predicts that language from visual state and action intent, and uses a diffusion model to render the consequences.
So the key claim is that explicit transition reasoning makes a video world model more physically coherent and more reusable.
That is the claim, and the benchmark results support it while also showing the boundary. PhiZero is a strong learned interface for visible state changes, not yet a complete symbolic theory of physics. That wraps up our explanation of PhiZero.